evening, participants. Today we have among us Dr. Atanu Nath, who is currently working as an assistant professor at Tihu College. So he will deliver the inaugural talk on the brand new theme of nuclear and particle physics, which is actually the seventh talk in our talk series, Padartha Bigyanar Itu Aru Bohutu. So the title of his talk is A Magnetic Story, Waiting to Reveal the Hidden Code of Nature, which is basically about the exciting results from the Muon G-2 experiment. So Dr. Nath did his BSc in Gurucharan College, Silchar, and thereafter completed his master's from SN Bose National Center for Basic Sciences, Kolkata. He was then at TIFR Mumbai in a research position before moving to University of Naples, Federico II in Naples, Italy, for a PhD. After completing his PhD, he worked as a postdoctoral researcher in Italy and USA on the Muon G-2 experiment at Fermilab as a run coordinator for the Italian team. He also worked as a postdoctoral researcher at IIT Guwahati on the NOVA and DUNE experiments, which are two cutting-edge neutrino experiments of our time. And we are, of course, excited to hear more about these experiments in the talk. So, students, please feel free to interact with the speaker and ask him any queries you might have, not only science-related questions, like I always say, but career-related queries as well, because he has vast experiences at top institutes of India, such as TIFR, SNB, and CBS, HRI, IMS, HNI, and so on. So, and also experiences of applying for PhD in Europe. So please throw in any career-related questions as well. And of course, any questions you might have on high-energy particle physics. So over to you, Dr. Nath.
Thank you, Himanshu. I'm really thankful for this, giving me this opportunity to talk on this platform. I mean, Padartha Bigyanar Itu is an amazing endeavor here, actually, in this area, where you bring all the global research. And especially, I thought this is, I mean, especially for local origin people, right? Give some sort of sense of connection. So this is extremely motivating. This is going to be, this is really, I mean, students are really lucky for such an amazing talk series. And I'm really happy to be a part of it. I usually attend most of the talks. Sometimes maybe I can't join one or two for some other, I mean, work-related reasons. But this is really amazing. So good to see that this is going to be big someday. It's already. So my talk today is about the Muon G-2 experiment. And the way I designed it is aimed at undergraduate students, but the problem is that this topic G-2 is already G equal to 2. I'll come to that. Is a quantum effect purely, quantum mechanics, let's say. But then G-2 part is 100% a quantum field theory effect, and so taking undergraduate students to there is I mean, it's a terrifying job. And usually I gave this talk offline in front of students. That really helps with body language, and I can show with toys and things, because spin is a very important part of this. And so rotational spin and how things are, I mean, precision and all these things. So, and then I gave this talk in front of experts, of course, online, and that's not a problem because everyone knows about it. But undergraduates, it's going to be difficult, but I will try my best, and that's why the talk is a bit long. So just bear with me as I try to proceed. So magnetic story, because it's about a tiny magnet, really, that a tiny magnet whose, let's say, magnetic strength we are measuring with an unimaginable precision. It's like the precision, like you're measuring the length of a football field with a hair, you know, a strand of hair. So that kind of precision, maybe more. So then, I mean, slight discrepancy that we are relying on slight discrepancy in that. So মানে মই অলপ অসমীয়াত অলপ ইংলিছ এনেকুৱা মিক্স কৰি কম এইটো আউটলাইন so I'll just skip it. So first হ'ল আমাৰ science কেনেকুৱা কাম কৰে. So let's say apple falls and we ask why do they fall, and then like we build a model, right? So Newton did. I don't know whether really the apple fell or not, but at least that's the story. So based on that, Newton gave a model of gravitational attraction. Now, that's good. That explains why it falls. But then based on this, you can predict like how much the apple will take to fall from the sky, right? From the branch to the ground. So this is an extra that comes from the model. And that's the prediction. And some other people then design experiments where apples or feathers and things are falling, and they measure this time of flight. Kiman time lagibo, to travel this distance. And then, so in this experiment, they measure the time of flight. And then using, let's say, Newton's gravity, we theoretically calculate how much time it should take. And then if the difference between these two, if the difference between this experimental measurement of time of flight and the theoretical measurements is bigger than some value, 5 sigma, that I'll explain shortly, not really in detail, then I'll say that, okay, if this difference is too big, then the theoretical model is unable to explain the actual observation. And so we really need a new model or, some corrections in the model. So 5 sigma, it's like roughly, that this difference could be due to an experimental blip in the data, a slight mistake or something, but the chances of that is like 1 in a million. Otherwise, 1 in a million chance that this could be just a blip in the data. But it's really 1 in a million that it's just a chance. So it's a really good measure that, yes, there is a difference between theory and experiment, and we need a new model. So the model that we are going to talk about today is standard model. Just like Newton's gravity. Standard model is the model that we are talking about today. And this time of flight is the magnetic moment of the muon. So this is the analogy. Just like the time of flight of the apple, here we'll talk about the muon's magnetic moment, and standard model will be our model in question that we're going to test. So about 20 years ago, there was an experiment, Brookhaven National Laboratory in the US. So, hey, Brookhaven Laboratory, muon or magnetic moment, really precisely তেওঁলোকে calculate কৰিছিল। কৰাৰ পিছত সেই টাইমত থিয়ৰিৰ যিটো ক্যালকুলেশন আছিল, থিয়ৰিটিক্যালি স্ট্যান্ডার্ড মডেলৰ ওপৰত বেস কৰি যি ক্যালকুলেশন কৰি ম্যাগনেটিক মোমেন্টেৰ যিটো ভ্যালু পাইছিল, তাৰ লগত experimental result 20 years ago, difference to আহিছিল about 3.7 sigma. Now we need 5 sigma to say that it's really different and we need a new model. 3.7 sigma is almost close to 4 sigma, so a little bit more, and we could say like, yeah, there is, do we need new physics, new model or not? And then this difference, is, it depends. Like, that there is always an error in the theoretical calculations where you take approximations and all these things, and also in the experimental data. So this broad, can you see that? Yeah. So this broad band represents the experimental error, while this blue band represents the theoretical one. And so if these bands shrink really, shrink, so that means like more and more precise and precise measurement. The yellow band, if it shrinks, means more and more, precise experiment. So the blue band means more precise calculation. And if these two bands shrink, you can see that the difference between them will increase, or they might not, because it's possible that they shrink and they come in this point, while these two shrink, this theoretical result shrink and they come here. So the difference becomes this. And so not much difference. But if they shrink in the other direction, like here, and they shrink in the other direction, then the difference could be more than 5 sigma. And then we can say like, we need new physics. The old physics does not explain this. But more precision means you need more and more data. You need better experiment with the new technology, and you need to take more data so that you have less uncertainty in the data. And you need better calculations. So usually in these calculations, we'll see that we need computers. So we're 20 years in the future now. We have better computers and better theoretical tools, mathematical tools available. So that was the aim. That, okay, almost 4 sigma difference ase. Etia better eta experiment korile, or better theoretical calculation korile, maybe difference to 5 sigma or beshi hoi jabo. In that case, we'll have new physics, science of new physics. So that was the aim, really. So to begin with, muon G-2. What are muons really? Muons are like electrons' heavier cousin, about 200 times heavier. Electron mass Ziman, that came almost like 200 times massive whole muon. Otherwise, they're absolutely same. Charge same, spin same, everything same, just heavier. Okay, just like electrons, a heavier version. And there are many particles in the standard model. We don't need to talk about them right now. Just remember that there are many particles and known particles. So there is a list of known particles like quarks, gluons, and taus, and neutrinos, and all these things. But they are known bunch, a collection, Higgs. Among those, there are lightweight particles, and they're called leptons. Electron is a lepton. Muon is also a lepton, slightly heavier. And then there is another bigger cousin, tau, which is also a lepton. And they have sort of other cousins. They're like really, really tiny. So they are like almost massless. Okay, so now we have a rough idea about muons. Now we'll move to what is G really in G-2. So any rigid body, if it's spinning and if it has some charge, so we know that it is like a magnet. Maybe from your higher secondary or I think second semester, that if you take a loop, a current loop, then it acts like a bar magnet. If you look from very up very distant, at a far distant away from the loop, it acts like a bar magnet. So the magnetic strength or magnetic moment of such a body with charge and that is spinning is given by this formula. You don't need to go into too much details of this. J is just current density. Okay. If we do some calculation like replace current density with charge density times velocity and all these things, we can derive a formula, a classical formula that looks like this. So if Q is the total charge in that body, and if M is the mass of the body, and if L is the angular momentum of the body, then the corresponding magnetic moment will be given by Q over 2M times L. This is a very simple formula. You can derive this in case of just an electron moving in a circle. Try to derive this. You can do this easily. And you can use the formula like current times the area, IA. Okay, so this is classical relation. This actually stems pretty far, even in quantum mechanics. So if we go to quantum, domain, it still is valid. Just We need to include just a factor G in front and we'll be okay. Otherwise, the formula is fine. So G times Q by 2m into M. Turns out that if we consider just an electron, and just imagine the electron is like spinning, like Earth spins on its axis, it's spinning, but it's not really spinning. So it's just an analogy. So just keep in mind that it's really not spinning, spin is something like charge. So like something has a mass, something has a charge, it has a spin, but you can imagine like something is spinning. And if that is so, for such a body, Dirac actually wrote an equation that explains the behavior of electrons. And if we look at Dirac's equation, you can see that it has a kinetic energy part and it has a potential energy part. And you probably know about this. If you put a magnet in a magnetic moment, so magnetic bar magnet, let's say tiny bar magnet, in a magnetic field, what is its potential energy? It's minus m dot b. Oh, the minus got lost in the black background. Sorry for that. It's minus m dot b. M is the magnetic moment of that bar magnet, and b is the magnetic field in which that particle or the magnet is. So now, if you compare this with the potential energy term of the Dirac equation that explains electrons, you see that this is like m, this whole with 2 and everything. This whole term is like m, and then we have dot b. And if we compare this with the previous result, then you see that this El is the charge of the electron, okay? 2ml is 2 times the mass of the electron. S is the angular momentum. So if we compare these two, then G is actually 2. So G turns out to be 2. So Dirac equation is saying that the value of G, the factor that we randomly put while going to quantum mechanics, must be 2. But is it really 2? So that's the question. Turns out if G was really true, then the energy difference between 2s half and 2p half orbitals of the hydrogen atom would be 0. So they would be exactly the same energy. You know these things from chemistry, right? S orbitals, p orbitals. So 2s half and 2p half would have exactly the same energy if G was 2. So G is not 2, really. And this actually earned the Lamb and Rutherford a Nobel Prize. G, that it's not equal to 2, fueled the development of something called the quantum electrodynamics. And these are the main protagonists. Feynman, you probably know about him, Schwinger and Tomonaga. So what does really G not equal to 2 then mean? Well, vacuum really has the answer. Now, we think classically that vacuum means there is nothing. Aconite, just emptiness, nothing. But that's not really true according to quantum mechanics. Vacuum is actually teeming with pairs of particles. Let's say electrons and its positive brother, let's say. It's called positron. So every particle, just for the really young students, every particle has its like an anti-partner. So electron has a positron. Proton has an anti-proton. Like what? So everyone has their another partner. If they meet, they destroy each other and become pure energy. Okay? So in the vacuum, what is happening is constantly this electron and its anti-partner is popping up and then destroying each other. And happening, like it's repeating. And not just electrons, all sorts of particles and their anti-particles are popping up and getting destroyed. This is happening all the time. And this is happening in a way that we can't directly detect them because they're like hiding. So before you detect them, they destroy each other. This tiny time within which this happens is constrained by something called the uncertainty principle in time and energy. So if they're very massive particles, then they really survive for much less time compared to if they're very light particles, then they can stay for longer. Okay, so longer the time, less their mass, shorter the time they survive as a pair, before annihilating each other, they're lighter. So it's happening something like this.
Certainty principle. We have particles that come in and out of existence. They're just a blip. So they come in and then they vanish again.
So they're like appearing and vanishing.
And so as our muons are going around, they're not only.
So when the muons are moving through space and time, they interact with these, virtual particles. So, I mean, we don't see them directly, but the muons, the quantum particles, they are seeing those other particles. So muon is moving, electron and its antiparticle come into existence and, interact, talk to the muon, and they disappear. And then some other particles, quarks, some, neutrinos, some tau, some other muons, these are also coming and interacting with it. So all the time, muon is surrounded by this cloud of, virtual particles and their antiparticles in the vacuum. And that's why their behavior gets sort of shielded, It's like they're covered by a cloud. So you don't see them as a bare thing. So it turns out that if this cloud was not there, then G would be exactly equal to 2. And if there is a cloud, then G should be slightly more than 2. So vacuums, these unknown interactions give rise to this effect that G is not exactly 2. And these things are very much quantum field theory effect that I will not go into too much of depth today. If anyone is interested, can of course contact me and we can discuss later. We need to discuss something like Feynman diagrams. These are not the diagrams by Feynman that we're going to talk about today. So not in depth, just consider a few things. Like Feynman had a nice way, of replacing big calculations with some simple diagrams. These things are called propagators. So some electron is going in this way, some positron is moving in this way. This is a photon or light moving in this way. They're given by these symbols. Then you can join them. You can join two electron lines and a photon, and you can get these things. This is the only way you can join these three in quantum electrodynamics. So don't get scared by these things because we are not going to calculate these things. Some vague idea that people use these diagrams to calculate big mathematical expressions. So, for example, the first one, if it is like this, it means an electron comes, it emits a photon, and just moves on. And then this means a positron absorbs a photon and moves on. And this means a positron and electron coming, annihilating each other, and they're converting into a photon, and so on. There could be diagrams like this. So there are like two possible joining on both sides. Like here, one combination, here another one. So this actually means like an electron and a positron coming, annihilating each other, becoming a photon, and then that photon then again converting into a pair of positron and electron, and so on. Okay. Then there are diagrams like these, like where a photon is coming and then a loop of electron in the middle, and then another photon. These are the particles that are in the loop. They're called virtual. They're virtual. They're not real. So they actually represent those particle-antiparticle pair in the vacuum. So popping up. So actually this means a photon is just going on with its own business, but in the middle, it interacts with, let's say, an electron, and its antiparticle. And so it will have an effect in the life of photon. These loops can be anything. It can be photon. Here in the loop, we can have electrons, muons, or there could be particles that we don't know about. So physicists don't know about. These unknown, strange particles could be also there because this is reality, right? This is not theory. This is in the vacuum. There, all sorts of particles and antiparticles are coming into being and annihilating each other. So in principle, particles that we know about, they're also doing this, but there could be particles that we haven't known yet. Those also will be there. And so through the, the muon passing by and how those unknown particles are interacting, we could get some ideas about who are those unknown, guys. Okay. The good news is the calculation. Okay, so calculations of these loop diagrams are difficult, really difficult. There could be one loop, there could be many loops, loops inside loops, extremely complicated. But the good news is that they are very less important, at least in quantum electrodynamics. These guys are easier and they are more important. Like they give bigger terms, bigger numbers. And these things come as loops, come as corrections, small corrections. So they're less important. More and more loops means less and less important, So this is the good news. We don't have to calculate too many of them. More complicated diagrams with more vertices, more loops, they're less important. So now coming back to the G minus 2. So turns out this diagram, imagine like this is an electron, this is an electron, and this is a photon. This particular diagram gives you the value as G equal to 2. And if you consider like slightly more difficult, so there is no loop, right? You see, there are no loops inside. But this is sort of the first loop. And this starts giving, and another one like this, these start giving G's values slightly more than 2. So this gives G equal to 2, but then you start taking care of these loops, that is those virtual particles, mysterious particles in the vacuum, and you get value of G slightly more than 2. So Schwinger was the one who first calculated, these first of few loops. And he found the value of this G equal to slightly more than 2. This slightly more than 2 term is alpha over 2 pi. So alpha, is called fine structure constant. It just means that how strongly particles interact. So for example, how strongly electron repels another electron, or how strongly electron attracts a proton. So alpha represents that strength. So it turns out that G minus 2 divided by 2 is this alpha over 2 pi. We call this the anomaly. So if G equal to 2, so G equal to 2 is of course 0 term, and then you have this slight correction. Schwinger calculated this slight correction, and he explained, a lot of theoretical results, like why these 2s half and 2p half energy levels of hydrogen have different energies. And it is so important. So turns out that this is like 0.00232. So, I mean, G equal to 2 plus this 0.00232, this tiny number. It was so important that alpha over 2 pi, this extra term that he calculated, got engraved in his grave. I should speed up, otherwise I will not be able to finish within an hour. So the thing is, so if you consider like the s orbital or shape to Kaneko, spherical symmetric, while p orbital is not spherically symmetric. It has a different shape. And so in the vacuum, the s orbital gets kicked by these particles differently, virtual particles, compared to the p orbital. And because they get kicked differently, so their energy gets modified differently. So they have different energies. Okay. Now the loops are very important actually. As I told you, that vacuum of actually a virtual particles বিলাক আৰু তাৰ anti-particles বিলাক এনেকুৱা pop up হ'ব আৰু destroy হ'ব. So known particles বিলাকো থাকিব আৰু unknown particles. আর সেই interaction বিলাক hidden আছে আমাৰ এই loop diagram বিলাকত. Okay, so loop diagrams are, that's why important. They have the hidden information. So loop diagram eta all the known particles, we can consider all known particles and we can calculate these loop diagrams. They will represent the theoretical result due to the standard model particles. Now, etu hobo amar theoretical result. Eti experiment korile, of course, unknown particles jebilak, they are unknown. Hey, unknown bilakor pora contribution ahibo. They are also kicking, right? So theoretical result aru experimental result majot era difference ahibo if there are other particles that we don't know about. Okay, so this extra part, actually the anomaly that I said, extra part is the G-2 part, right? A extra part eta part thakibo amar known particles bilakor karone, a green part to yat ahibo amar quantum electrodynamics, something called hadronic. We don't need too much details. They're there because of quarks and all these things. Strong nuclear force and weak nuclear force. So এই তিনিটা মানে contribution ধরিলে, this is like the known physics. This is the known physics. It's called standard model. তারপর calculation আহিব এই loop blobot. So this is known, and there will be a part which is not known, new physics. That will, of course, not show up in the theoretical result due to standard model, but is of course going to show up in the experiment. On experiment, it doesn't know about what is your standard model, what is known or unknown. Experiment means real nature. So real nature has unknown particles. Hello, any question or something? Kiba ase neki? Okay. So unknown particles, experiment korile, of course, unknown particles are there in nature. So they are kicking, so they will show up. And so we'll have the difference between a theory and experiment. But the point is, theory calculation extremely precise hobo lagibo. An experiment to extremely precise hobo lagibo. Only then we'll be able to see this tiny difference. And that tiny difference will tell us about the tiny contribution from the new unknown particles. Now, imagine like a loopot unknown বা known যিকোনো particle আছে. Okay, so loop মানে কি? Vacuum particle antiparticle এটা produce হইছে, pair annihilate হই আছে. এই particle এটা mass আছে, of course. Let's call that M loop. Any electron hobo pare, muon hobo pare. It could be tau electron nisina aru heavier. Muon or like 16 times heavier than muon. So a looper pora mane a massor jitu contribution ahe. Mane looper to the z particles to enekwa, popping up and destroying. If the mass is M loop, then aru e particles jitu mane goi ase. Let's say muon is moving, right? We are today considering muons. Only muons are moving in vacuum. So muon or mass to uporot hobo. L is the muon mass. Okay. Now question is, new physics or mane ki? Mane unknown particle. Tar mane ei looper mazot unknown particle ki eta ase. So tar contribution to tolot ahibo. That means m of muon's mass square divided by m of unknown mass square. Now, unknown particle mass to control koribo noaru. It could be very heavy something. It's possibly really heavy. And if it is heavy, then amar numerator to dangor hobo lagibo. Only then contribution to bigger and bigger and bigger hobo. So we'll be able to measure this, better. Otherwise, I mean, if you take it is electron, then electron divided by some really heavy particle, tar mass or square kiman hobo, almost 0. So that's why electron consider nokoru actually. That's why we are considering muon. Because electrons mass square divided by unknown heavy mass square will be almost 0. So we are considering muon because muon is heavier. So all of dangor hobo in term 2. But then, why not tau then? Why not tau, right? Tau is 17 times heavier than even muon. Why not tau? The problem is that tau really dies quickly. So even muon survives for only 2 microseconds when at rest, and tau dies in like roughly 0.3 picoseconds. So we don't have that much technology that we can store taus and do our measurements. They die much before we even think about designing any experiment of that, precise. So that's why tau would be amazing, but the technology yet is not available to deal with these fast dying particles called taus. Okay, now known part of physics, I said. Known part has 3 parts. They're called QED, quantum electrodynamics. It is due to electromagnetic theory, Then there is something called weak term. Weak is due to weak interaction. Mane nuclear decay, fike, jibilak force or karone hoy. Tar eta term ase. Another known term is called hadronic term. That is due to strong interaction. Strong interaction we really don't like. Remember, we actually more and more complicated diagrams, loops, foops, Zibulak diagrams, they're less and less important. Well, that is not true for strong interaction. Turns out more and more complicated diagrams means more and more important. And they're difficult, so nobody knows really how to calculate them. Seriously, we don't know. So we're scared of strong interaction. There are many techniques, but they're approximate techniques. And as a result, huge errors are introduced in calculations because of these complicated, approximations. And so these are some of the approximations. I'm not going to discuss them in detail. One of them is lattice QCD, where supercomputers are used, but promising, really, very promising, this technique. That's why, theoretical results, in principle, theoretical result could be infinitely precise, right? No error at all. Don't approximate. And then no errors. Point value, no error bar, precise. But we can't do that because calculations are difficult, extremely difficult. No mathematicians in the world can do that. And so they approximate. And due to those approximations, some theoretical errors enter in the game. So, so we can write this complete result of G minus 2 divided by 2 as a quantum electrodynamics part, weak part, hadronic part, and the result, it turns out to be this. You can see it's very precise. There are how many numbers? 9 numbers, and then 2 more. Only in the last 2 digits, we have this error of 43. Okay, so this is extremely precise. Part per million. So part per million means, like, percentage means part per 100, right? 1% means 1 in 100. 1 part per million means 1 in 1 million. So the standard model, like theoretical calculation, and the experimental result from the Brookhaven National Laboratory, the last one, before 7th April 2021. So 2021. 2021 or 7th April or ago, a difference to kiman asil 3.7 sigma. Prothome moi koisilo eto. But it changed after 7th, April 2021. We'll come to that difference after that a bit later. So, bahut theoretical discussion korisu. Let's talk a little bit about, not little bit, almost 50% about the experiments. Now, theoretical all of gom paisu, ami let's say experimentally কেনেকুৱা actually আমি calculate কৰো এই magnetic moment of muon. All of history before that. First experiment হৈছিল 1957. Nevis cyclotron. Okay, that G equal to almost 2. Our তার মানে error যিমান আছিল it's huge, 100,000 per million. তার পিছত অলপ ইম্প্ৰুভমেন্ট হৈছে লিভাৰপুল সাইক্লোট্ৰন 1957 কিন্তু এরর আছিল 6986 part per million, almost 7,000 part per million error, big error. CERN first experiment হৈছিল 1961. So that G equal to slightly more than 2 পাইছিল, but the error was about 5,000 part per million. We'll get some idea about what is part per million. I mean, key to important. ETIAS is like 5,000, 7,000 part per million, about 1961. 1968, 5,000 jump kori, error to reduce 266 part per million. Then there was a huge jump again. CERN 3 experiment 1979. It was 266 or 7 ppm part per million error size. Okay. Then it was below 1. I want to look at the national accelerator. 2004 result. So then what is our aim? Our aim actually, Fermilab did a new experiment. I mean 0.14 ppm jump. Almost 4 times more precise experiment. I mean, horrible like that. Why? Because 3.7 sigma difference between experiment and theory. It's encouraging that our own precise experiment maybe difference to baribo 5 sigma. Then we'll get some idea about the new physics. So it was a big move, through sea, then river, then road travel. Hey, Brookhaven experimenter for Fermilab. You can see the road distance is not that much, but it was a dangor magnet, 14-meter diameter or at a magnet, when a big at a taller size or magnet. Aru magnet or slight damage hole amar bahut problem hobo. And I mean 0.1 part per million. Eta sulidi kote football field measure kori 1, 2, 3, 4, like 1 foot, 2 foot, 3, 1 foot, 2 feet, 3 feet. Likewise, eta just one hair strength the measure for that much precise. So it needs a perfect magnet. All of damage, bend, we cannot afford that. Through water movement to basic horrible or through highway, really slowly, say as a traffic jam farm hoy, yet gote road loi, gote experimento karne belek traffic road bondho ase. Then quite important. You can see the movement here.
2013, an enormous 50-foot magnet traveled 3,200 miles by land and sea from Brookhaven National Lab in New York.
যেতিয়া Fermilab আহিছিল,
This magnet is
thousands of people that জমা হয়তো welcome কৰিছিল actually. So a strength of the magnetic field of this magnet is about 100 times the strength of fridge magnet. Fridge of magnetic photo stylist magnet lagai tar comparison normal amar magnet bilakor comparison almost 100 times stronger. So edu hol Muon G-2 experiment of Fermilab. It's a small collaboration, about 200 collaborators, 7 countries, 35 institutions. Moi actually Italian collaboration or join korisilu. I was stationed in Italy, and I mean to and fro. So 1 month in Italy, 2 months in Fermilab, like that. So it's not really compared to any particle physics experiment. This is a small collaboration, really. Everyone knows everyone else by name. So it whole our Italian, collaboration, really small. So that's me, and he is the spokesperson of G-2 at that time. Graziano Venanzoni. He's a really big scientist, top 2% or I think are the top 5 scientists that we are looking forward to. So probably Nobel. Okay, so this is the Italian collaboration. আমি a collaboration meeting of RNA. We gathered at Fermilab together. So this was the picture taken. Anyway, this is the one part of the Fermilab. Google Map or Azi screenshot. Actually, you can go and search Fermilab and look at the various campuses and buildings and facilities at Fermilab. So before I go, actually, I may discuss for him. Okay, it got jammed. Give me a minute. Let me reconnect. Okay. So, okay. So actually, I do hold Tevatron, the second largest particle accelerator, ASIL, and now it's not working anymore. So yet linear accelerator it has. So how it works? Linear accelerator, we accelerate hydrogen ions. Hydrogen ions basically means protons. We remove electrons and it becomes hydrogen ion. So protons. Protons then go to booster. Booster or go boost hoy. 400 MeV proton becomes almost like 9 GeV. And then they are made to hit a target. So then then it goes to a recycler. There it recycles, and then proton or bunch create hoy. That bunch comes, and then it hits somewhere here, a target. It hits. So when proton hits the target, it produces, because total kinetic energy to almost their potential energy convert hoye jay, right? That energy produces a lot of particles. That kaons bully particles ase, pions bully particles ase. Hey, pion particles bilakor pora decay hoy muon particle create hoy. Hey, muon particle amar this path. This is the beam line. Your delivery ring. Your pora goi. Goi muon campus. This is called muon campus. Muon campus of enter kore. Tar pisot muon is a magnet to ase. Magnetor bitot homai. It circles. And then they decay into positrons, and we detect those positrons. And I'll come to that. How those positrons tell us about the magnetic moment of their parent muons. Okay, just shortly covered that. So yet, an interesting concept amar lagibo. It's called parity violation. Parity violation, what it is, I'll not go to that again into details. It's a bigger subject. Let's just say that there are first 2 kinds of particles: left-handed or right-handed. Left-handed mane hol particle or ki ase? It's moving, right? So tar eta momentum ase. Particle ta move korle tar momentum thakibo. And it has a spin. So spin or direction, jodi momentum or direction not hoy. For example, particle eneko move kori ase ar tar spin eneko. Then spin or direction or momentum direction eke direction of. In that case, it's called a left-handed particle. Aru jodi hitu opposite hoy, mane spin or direction, momentum or direction eitune, kintu spin eneko pori ase. Then spin or momentum direction or opposite, we call that right-handed particles. Yet aro complexity ase, chirality, helicity, ibilakot etia jabo noaru. Tomaloke at least all of quantum mechanics at least advanced finish koribo lagibo for that. But for now, the piece of information that you need is that all the particles that we see in nature are left-handed, and all the antiparticles are produced right-handed. But we can actually so spin aru a momentum or direction to we can change. So let's say spin enekwa kori ase aru enekwa move kori ase. I can run faster and faster and I can outrun this particle. At that point ki hobo momentum or direction with respect to me opposite hoi jabo because I am faster kintu spin or direction same thakibo. So eta left handed particle right handed hoi jabo pare, right handed left handed hoi jabo pare. But at birth, so if they're really high energy, particles usually will be left-handed. Antiparticles, are antiparticles it is, electron or positron, they will be right-handed. But if the particles, so itu kenekwa hobo, outrun, when can I outrun a particle? If it is massive, particle etar mass thakile, I can run faster than that particle and I can flip the direction of momentum. But if the particle is massless, then we can't do that. We cannot outrun a massless particle. A massless particle travels at the speed of light, and we can never move at the speed of light. And so, faster than speed of light is beyond question. So we can never outrun a particle moving, a massless particle. And therefore, massless particles are always left-handed, always. And massless antiparticles are always right-handed. One example is neutrinos. Okay, neutrinos are like almost massless. Okay, so parity violation says that particles are left-handed, antiparticles are right-handed. Okay, now what happens is, so protons hits the target, right? And they produce pions. Those pions have spin 0. They have spin 0. So electrons have spin half, right? Pions have spin 0. Put it here. So if pion is spin 0, when it decays into a muon, so pi plus actually decays into a mu plus. It's called an anti-muon, but just ignore the fact. Mu plus, muon. It produces a muon and a muon neutrino. So obviously, muons have spin half, and neutrinos also have spin half. Spin means angular momentum. So angular momentum must be conserved. So before it was 0 angular momentum. Finally, after they decay, total angular momentum has to be 0. But we know that from, as a fact, that neutrinos are particles, and so they are left-handed. They are left-handed. There is no option. So if the neutrino is moving in this direction, its spin is in the opposite direction. And that means to cancel this angular momentum, the produced muon will have to be also left-handed. You can think about this. Just take mu plus at pi plus at rest, a body decays into 2, one moving in this direction, other moving in this direction. One spin is in this direction. Just think about what the other spin has to be. It has to be in this direction. It also has to be left-handed. Otherwise, cancellation will not happen. So the produced muon is left-handed. There is no other choice. All muons produced are left-handed. Now the next step is this mu plus, left-handed mu plus, decays into 3 particles. One is positron, E plus, and one muon neutrino, which is an antiparticle, and an electron neutrino. So anti-muon neutrino and electron neutrino. These are probably getting too complicated, but just consider that দুটা neutrino produce hobo. Eta antiparticle, eta particle. তার যেহেতু antiparticle, সেইটো right-handed hobo লাগিব. যেহেতু এটা electron neutrino particle, সেইটো left-handed hobo লাগিব. And it turns out muons are moving really fast. So fastest যিবিলাক electron produce hobo. Fastest. সেইবিলাক obviously muons directionত move কৰি আছে, সেই directionত produce hobo. On opposite directionত যিবিলাক electron positron ulabo, their velocities will get cancelled out. So there will be less energy, there will be low energy positron. It's like, you are running and throwing stones in both directions with equal energy, let's say. So you are running in this direction. So the stones that you are throwing in forward direction will be faster compared to the stones that you are throwing backward. On cancel hui ase, dui directional velocity. So if we consider the stones, here the stones are, positrons. Those will be higher energy and fastest energy, the highest energy positrons. They will have to be right-handed. Again, due to conservation of angular momentum. Because A duta right-handed, eta anti-particle, eta particle. So eta right-handed, eta left-handed. So tai right-handed to cancel koribo lagibo. Aru eta beleg direction of right-handed positron. Kyo? Can't initially, prove korisu. The muon was left-handed. So finally, it has to be, the whole system has to be left-handed. So right-handed duta cancel hobo lagibo. So that totally left-handed palm. And that's why the produced positron in the forward direction has to be right-handed. So tar mane ki? Mane hol je muon asil right-handed, left-handed. Mane muon ei directionot move kori ase aru tar spin opposite directionot. Kintu decay hoise jitu positron hetu right-handed. Tamane hetu z directional move kori ase, the spin or same direction. That means what? The spin forward direction. Aru muon or spin ki backward direction. Kintu muon or momentum forward direction. So turns out, amar electron or jitu direction hobo, direction, it's directed along the spin of the muon. So it's interesting. Karon eta enekwa torch nisina hoi jabo. If you have a torch, so you are moving the torch like this, okay? So torch or light ulai ase. So it is like the muon is like a torch, okay? Tar spin z direction ot ase, hey direction ot positron bela ulabo. So spin jodi enekwa kori thake, electron enekwa onaka ghuri ghuri will get ejected. So his electron ami pam, electron or positron, sorry. Hey positron or direction to gompale, I'll know about what was the spin direction of the muon. So actually spin pale ki pam. Spin mane spin or pora magnetic moment. So electron or positron jitu ami capture kori will know about the spin of the parent muon from that. So how do we do that? There are two things when a charged particle moves in a magnetic field. Two things happens. I think you have found this, the charged particle at a magnetic field dot introduced korile, it moves in a circle. It moves in a circle. But, so this is one sort of oscillation, right? Circling, rotational motion. But there is another motion, which you will get in advanced electrodynamics, actually. Not yet. It is like a precession. So, like top enekwa ghora le ki hoy. Top to spin kore, but it also wobbles like this. So, yat ki hoy, the muon is entering and it's rotating, but it's also precessing like this inside the ring. So, ring or bhitorot magnetic field ase, right? Ring or bhitorot magnetic field ase. And so magnetic field dot muon to ghuribo enekwa, it will rotate, right? But it will also precess. So enekwa kori thakibo. A precession to hobo around tar momentum, around momentum. So enekwa goi ase, ar tar around enekwa kori ase, enekwa kori. So mane spin to enekwa kori jabo. It will be like this. That's why an offline demonstration is really effective for undergraduate student. Anyway, so yeah, duta actually periodic motion ase. Eta rotational, aru eta hol tar momentum or around the enekwa je kori. Mane arthon nisina. Ar tenekwa kori guri ase around the sun, let's say. wobbling and round. এতিয়া টার্নস আউট তোমাৰ এই দুটা স্পিন মাজত স্লাইট ডিফাৰেন্স আছে, এই দুটা অসিলেশনৰ পিৰিয়ডৰ মাজত স্লাইট ডিফাৰেন্স থাকিব if g is not exactly equal to 2. g যদি 2 ইকুয়াল হৈ যায়, then এই যে রোটেশনৰ যেটো পিৰিয়ডিক মোশন আছে আৰু হিটো যেটো আছে, they will be exactly same. আর অলপ ডিফারেন্স থাকিলে it will say that g is not equal. So আমি actually the difference in this frequency turns out to be this complicated term. Etu বহুত easy term এনেকুৱা হ'ব, but if we consider এটা electric field কিয় লাগিব? তোমাৰ beamটো focus কৰাৰ কাৰণে electric field লাগে. Just magnetic field থাকিলে simple, but electric field কি থাকিলে হ'ব? এই ডিফাৰেন্সটো হৈ যাব slightly, এটা electric field term আহি যায়। যেটো cancel হৈ যায় if we take precisely 3.1 giga electron volt energy যদি আমি মিউন কনসিডার কৰো, then electric field termটো cancel out হৈ যায়। Okay, and then so this represents that. So দুটা frequency perfectly match করিলে আমি কি পাম? দুটার exactly মানে let's say এই পয়েন্টত আমার স্পিনৰ ডিৰেকশন এনেকুৱা আছিল আৰু মোমেন্টামৰ ডিৰেকশন এনেকুৱা, এটা ফুল রোটেশন কৰি আহি ইয়াত যদি দুটাৰ ফ্রিকুয়েন্সি এক্স্যাক্টলি সেম হয়, সেম ডিরেকশনত থাকিব, বাট যদি দুটাৰ ফ্রিকুয়েন্সিৰ অলপ ডিফারেন্স হয়, দেন কি হ'ব? এই রোটেশন আর এই রোটেশনৰ টাইমিংৰ অলপ মানে আর ডিফারেন্স আহিব। ইন দ্যাট কেস ইয়াত এতিয়া আছিল like this, then it will turn and come back and maybe it will be directed in that direction. এতিয়া ইন্টারেস্টিংলি আমি কি কৰিছো, ভিতৰত ডিটেক্টৰ ৰাখিছো ইয়াত ডিটেক্টৰ বিলাক। সো ডিটেক্টৰস এনেকুৱা আছে ভিতৰত, আউটসাইডত নাই। তেতিয়া কি হ'ব? at some point আমাৰ ইলেক্ট্ৰনটো এই ডিৰেকশনত ইন্টেৰিয়ৰ ডিৰেকশনত থাকিব, দেন এটো এটা টাৰ্ন কৰি ঘূৰি আহিব, এন্ড যেহেতু দুটাৰ অসিলেশনৰ ফ্রিকুয়েন্সি স্লাইটলি ডিফারেন্ট, নেক্সট টাইম that direction to will be slightly off, maybe towards outside. So ebar ami pam eta peak in the number of positrons that we receive in the detector. Next time we'll not see any positron coming in our direction, so there will be a down, peak and drop. So eta oscillation pam ami, hey oscillation to thakibo only if g is not equal to 2. If g equal to 2 ami flat pam, flat, always same value, কারণ ম্যাচ করে যাব ঘুরি আহি। and there will be another exponential over it, কারণ হল initially যিমানখিনি মিউন আহি actually সোমাব আমাৰ ৰিঙত, next time some of them has died out, next time more died out because decay হৈ আছে, so there will be an exponential and an oscillation over that. এই oscillation টার্মটো আমি mathematically fit করি, ম্যাথমেটিক্যালি ফিট করিলে তারপরা আমি অ্যাকচুয়ালি এই ফ্রিকোয়েন্সির পরা ওমেগা এ বলি ডিফারেন্স ইন ফ্রিকোয়েন্সি পাই যাম। আর ডিফারেন্স ইন ফ্রিকোয়েন্সি পাই গলে উইল নো ডিরেক্টলি অ্যাবাউট জি মাইনাস 2, কারণ এই ডিফারেন্স ইন ফ্রিকোয়েন্সির লগত ডিরেক্টলি প্রপোর্শনাল আছে জি মাইনাস 2, সো উইল নো অ্যাবাউট জি মাইনাস 2. অফকোর্স দের আর কমপ্লিকেটেড ইস্যুস, কারণ তোমার বিম টু যে মিউনৰ বিম পারফেক্টলি ফোকাস হৈ সেন্টারত নাই, অলপ মানে অসিলেট কৰি থাকে due to imperfections in experiments. So সেই কারণে আমার corrections কৰিব লাগে, that's complicated. Sometimes মিউন সেন্টারত না থাকি সাইডত লাগি যায়, তো অলপ লস হৈ যায়, তার কারণে এরর্স আহে, সেইবিলাক কনসিডার কৰিব লাগে। Sometimes ই ফিল্ড, ইলেকট্রিক ফিল্ড যেটো আছে তোমার ফোকাস করার কারণে, সেই ইলেকট্রিক ফিল্ডটো ইলেকট্রিক ফিল্ড থাকার কারণে আমার এনার্জি ডিফারেন্স এক্স্যাক্টলি 3 GeV নহয়, তার একটা স্প্রেড থাকিলে সেই ইলেকট্রিক ফিল্ডৰ এফেক্টৰ কারণে ক্যান্সেলেশনটো পারফেক্ট নহয় যেটো হয়েছিল। সো সাম এরার্স, এইবিলাক ডিটেইলছত যাব নালাগে, জাস্ট এক্সাম্পলস দ্যাট কিমান কমপ্লিকেটেড আৰু কিমানখিনি এরার টার্মস আছে তাত। আর সামটাইমস আমার পারফেক্ট সার্কেল পাব লাগিলে কি হ'ব, ভেলোসিটি যেটো আছে চার্জ পার্টিকুলার ম্যাগনেটিক ফিল্ডৰ লগত পারপেন্ডিকুলার হ'ব লাগে, but it's not in reality perfectly perpendicular, অলপ angle থাকি যায়, তারপর এটা error আহে, so we need to also correct for that. So there are terms like this, a lot of error terms. And then magnetic fields it was a ডাঙর একটা 7 মিটার রেডিয়াস ওর একটা ম্যাগনেট, তার ভিতরে গোটেই এই রিংটোর ভিতৰত absolutely stable same magnetic field ৰাখিব লাগিব, নহলে এই পাৰ্টত আমাৰ মিয়নে এটা magnetic field experience কৰিব, next পাৰ্টত বেলেগ এটা magnetic field experience কৰিব. So it's complicated, আমাৰ গোটেইখিনি result complicated হৈ যাব. So we need to make that really stable. Timer লগত চেঞ্জ হ'ব নালাগে, স্পেচত ইউনিফৰ্ম থাকিব লাগে, আৰু তাৰ এৰৰটো absolutely minimum হ'ব লাগে. সেইকাৰণে বহুত ডিটেক্টৰ্ছ আছে ট্ৰেইনৰ নিচিনা ঘূৰি থাকে ভিতৰত, in some periodic breaks in 2-3 days. So এনেকুৱা মানে absolutely stable magnetic field লাগে, এইবিলাক লাগে. So in the end, just ignore this. The result has various terms. এইবিলাক বেলেগ বেলেগ গ্ৰুপৰ পৰা আহে. এটা গ্ৰুপে ম্যাগনেটিক ফিল্ড ক্যালকুলেট করে স্টেবল রাখে, আৰু এটা গ্ৰুপে ইলেক্ট্রিক ফিল্ড ওপৰত ফোকাস কৰি আছে, আৰু এটা ৰিসাৰ্চাৰৰ গ্ৰুপ আছে কেনেকুৱা ট্ৰেক কৰিম এই পজিশন বিলাক, আৰু আছে সেই মেইন কেম্পাছত বিম পঠাই আছে যে গ্ৰুপে, মানে বহুত গ্ৰুপস আছে নিজৰ নিজৰ পাৰ্টটো কন্ট্ৰিবিউট কৰি এই ফুল টাৰ্মটো দিয়ে। এই টাৰ্মৰ পৰা আলটিমেটলি আমাৰ G-2 ওলাই আহে। এতিয়া এটা বহু ইম্পৰ্টেণ্ট পাৰ্ট আছে। এক্সপেৰিমেণ্টত সাইণ্টিষ্টছ আৰ ৰিয়েলি অনেষ্ট, বাট ষ্টিল কি হয়, we are humans, right? So we have our subconscious bias. মানে আমি জানো যে G-2 ভ্যালু কিমান হ'ব লাগে, it should be slightly greater than 0, মানে G-ৰ ভ্যালু অলপ 2 কে বেছি। So আমাৰ যেতিয়া let's say ভ্যালুটো 0ৰ ওচৰত আহি আছে, সাবকনসিয়াসলি আমি কিবা এটা টুইক কৰি ৰিজাল্টটো আমাৰ ফেভাৰেবল ডিৰেকশ্যনত লৈ যাব বুলি এটা ট্ৰাই কৰিব পাৰে। ইটস পসিবল সাবকনসিয়াসলি, যিমান অনেষ্ট হলেও ষ্টিল এটা টেন্ডেন্সি থাকিব, এটা বায়াস থাকিব, আইদাৰ ফৰ অৰ এগেইনষ্ট। ওকে, দ্যাট উইল ইম্প্যাক্ট দি সাইণ্টিফিক ৰিজাল্ট। সেইকাৰণে সেই বায়াসটো এলিমিনেট কৰাৰ কাৰণে ব্লাইণ্ডিং বুলি এটা বস্তু আমি ইন্ট্ৰডিউচ কৰিছো। মানে ইয়াত আমি কি মেজাৰ কৰি আছো, ইয়াত আমি ফ্ৰিকুৱেঞ্চি মেজাৰ কৰি আছো, ৰাইট? Frequency of this, frequency difference of this rotation and this precession. তার মানে frequency meaning time measurements. Time korpora hai, eta clock korpora hai. Amar eta clock ase. GPS maintained really precise clock. Aro clock or ki thake? Eta frequency thake. Hei clock or frequency ami ki korisu? Eta external group ani. They are not from G-2. External group. They are absolutely unbiased. They have no idea about, they are not working with us. External scientist or group, Ani, Duizon, they go inside and they lock, they have their own locks, really secured locks. Hey, jar bhitorot amar clock to ase. Etu khuli clock or frequency slight eta unknown shift kori. Kiman shift korise? Etu note kori. Eguloke lock kori olai hoise. Now, only these two guys know about this shift in frequency. Etia ami jetia calculation korim, amar result etia a clock or frequency termot ahe. So we have no idea about what it corresponds to actual frequency value, omega, ba G-. So even how can we be biased? We have no idea about amar eta number ahibo. That number is not G-2. Clock or frequency termot eta number ahibo. And clock or frequency to তেওঁলোকে আহি চেঞ্জ কৰি দিছে। কিমান চেঞ্জ কৰিছে we don't know. এটা শিফট কৰিছে, শিফটৰ ভ্যালু আমি নাজানো। সো আননোন এটা টার্ম শিফট বলি তাত সোমাই দিছো। এই শিফটটো আমাক তেওঁলোকে আহি যেতিয়া দিব, এই ভ্যালুটো বহালে তেতিয়াই আমি G-2 ভ্যালু ক্যালকুলেটেড মানে মেজার্ড ভ্যালুটো পাম। ওকে, সো as they are not giving us this value, so an unknown factor thaki jabo at the last moment porjonto ami na janu actually G-2 value ki. So even if we want, we cannot be biased. Even subconscious cannot be biased. So this is an interesting way to eliminate bias. So you can visit this. Why is the Muon G-2 experiment shifting time? Interesting at a YouTube video. Salegon aru next double layer আমি আরো ইন্ট্রোডিউস করিছো bias to eliminate করার কারণে। এটা তো হল হার্ডওয়্যার ক্লক ব্লাইন্ডিং, মানে ক্লকৰ ফ্রিকুয়েন্সি শিফট হয়েছে। আৰু এটা কি কৰিছো, আমাৰ এনালিসিস যিবিলাক কৰে, ডেটা এনালিসিস মানে 4টা বেসিক্যালি গ্রুপ আছে। রান 1 যেটো 2017 2018 যি ডেটা কালেকশন হয়েছিল, তাৰ যি এনালিসিস হয়েছিল, তাত 4টা ইন্ডিপেন্ডেন্ট গ্রুপ আছে। ইউকে গ্রুপ, 2টা ইউএস গ্রুপ, এটা ইউৰোপিয়ান গ্রুপ। তেওঁলোকে কি কৰিছিল, এটা গ্রুপৰ ইন্ডিভিজুয়াল এটা আৰু শিফট আননোন ৰাখিছিল। তার মানে বেলেগ বেলেগ গ্রুপৰ বেলেগ বেলেগ রেজাল্ট ওলাব, এন্ড দেয়ার ইজ নো ওয়ে দে ক্যান কম্পেয়ার, কারণ আননোন ফ্যাক্টর এটা নিজৰ নিজৰ সোমাই দিছে। সো বেলেগ বেলেগ নাম্বার আইছে, এন্ড দে ক্যানট কম্পেয়ার দেম আনলেস ওয়ান গ্রুপ টেলস দি আদার গ্রুপ what is this unknown factor. So it is called a relative unblinding. It is second layer. It even they share করিল নহব, কারণ আলটিমেটলি বাহিৰৰ পৰা সাইন্টিস্ট আহি যেটো ক্লক ব্লাইন্ড কৰি দিছে সেইটো কি জানেন। দেন থার্ড লেয়ার হল আমাৰ এই ডেটা এনালিসিস যেটো আমাৰ G-2 গ্রুপ আৰু ম্যাগনেটিক ফিল্ড যোনবিলাকে মেজার কৰে, তেওঁলোকৰ মাজত আৰু এটা ফ্যাক্টর হল আননোন ফ্যাক্টর সোমাই দিছে। তো রিয়েলি মানে আমি কিমান ট্রাই কৰো যে we should not be biased. This is the dedication, really, that we do not want to fool ourselves and fool the world. We're really sincere scientists, and that's why these steps. Okay, so in the end, ignore those complicated calculations. The unblinding. 25th February, we are very close to the end, so just bear with me. 25th February 2021 at a Zoom meeting hoise. Collaboration and all members start আছে। কথা আছো মই নাজানো somewhere। আমি তেতিয়া ইয়াত নর্থ গুৱাহাটীত আছিলো actually। So ইয়াৰ পৰা জয়েন কৰিছো through Zoom. Oh, that's me. Long hair, yeah. So মানে Zoom meeting কৰি তাত সকলে একেলগে আহি এনভেলপৰ ভিতৰত সিল কৰি আমাৰ এই যে এক্সটার্নাল দুইজন আহিছিল লক কৰাৰ কাৰণে, these two scientists, তেওঁলোকে এটা এনভেলপৰ সিল কৰি এই যে শিফট ফ্যাক্টর যেটো লক খুলি কৰিছিল, এই শিফট ফ্যাক্টরটো আনি দিছে এই মিটিংত। এনভেলপটো in front of everyone খোলা হৈছে, কম্পিউটাৰত প্রোগ্রামিং পাইথন এটা প্রোগ্রামিং খুলি রাখা হৈছে, আননোন ফ্যাক্টরটো এন্টার করা হব, G-2 রেজাল্ট ওলাই আহিব। তার আগত nobody knows, spokesperson নাজানে, nobody knows about what it's going to
Now,
be.
after 4 years of assembling and calibrating the magnet,
By the way,
and more than a year of data collection and analysis,
এইডি আহে নাকি
G-2 collaboration has
অডিও
its first result.
নাজানো, অডিও আহে।
The unblinding is
The
incredible.
audio is playing. Problem নাই হোৱা।
We finally agreed the analysis was complete, and we had to what we call open the envelope, where the secret decipher code is. So that number then got typed into a computer with nearly 200 people watching in a special Zoom meeting. Whoa! Wow! Yeah! Woo! The new result does not agree with the standard model prediction.
Does agree. See the standard model on the left side, and you see the new average of the experiments on the right side. There's a big gap in the white space. Bigger. This is what we mean by significance. Many people ask whether we have really discovered, but in our field.
So, audio আহি আছে নেকি নাজানো? Is it coming?
নাই, ভিডিঅ'টো অডিঅ'টো গ'ল।
Oh, that's it.
Oh.
So, at that moment, actually, first time we got the value of G-2. And as you can see, the 20 years ago result of 3.7 sigma difference আছিল. Now the value is 4.2 sigma. It has increased. তার মানে difference theory আৰু experiment difference to আৰু বাঢ়িছে. But it's still not, 5 sigma. We need 5 sigma to conclusively say that we most likely need a new theory. new physics to explain this difference. Of course, that was based on only, only run one data for collected over only 1 year. Tarpisot mui D-2 asilu actually up to the end of 2019. Yes, and the end of 2019. Then I resigned and came back and joined IIT. So we finished taking data. So almost like 19, so 17, 18, 19. So tinita ranor karne, actually, I was a part of this. Now run 2 and run 3 analysis almost at the end. So run 2 or run 3 is that just with run 1 data, 4.2 sigma difference I say. Now we really are expecting that with run 2 and run 3, it's 3 times more data compared to run 1. So a difference to increase 5 sigma cross kori jabo. In fact, we are aiming that total run jitu aru run mane 4 5 run 4 aru 5 or analysis soli ase actually start hoise just eibila kahile we are expecting them 7 sigma difference aibo. At least that's the expectation. So I think maybe in 6 months, at least in this year, we might get the result for run 2 and 3. Then that will be a big moment. I mean, 5 sigma jodi hoy, new physics discovery. Aru jodi even it turns out to be the difference has shrunk, then still it's a big result that there is no physics. So in any way, this will be a big result. This result was featured at the cover of Physical Review Letters, actually, for that month. And these are the 4 revolutionary publications that anyone can access. One is the PRL, the front, which explains the physics. Then there are, this has the gist. The PRD paper has the complete details of everything, like a huge paper, And then there is atomic nuclear physics, beam physics, based on those. These 4 papers are probably one of the most important papers in many, many decades. So, I mean, now, if there is new physics, there are a few models that are already available, supersymmetry. So, undergraduate students are karone moi hebilakot najao etia. Mane notun models manuhe bhabi rakhise already. So standard model mane hol amar known physics. Notun jodi G-2 experimental logot agree nokore tetia ki hobo pare. So hey notun corrections manuhe already there are some new theories. Hebilak ami tetia test koribo pare. Hebilake amar ei new term mane exact mismatch to explain koribo pare niki. So supersymmetry eta model ase. 2 Higgs doublet model, lepto quarks, and about data models. Aru bahut new theories ase jegula cancel hoi jabo if they cannot, explain this new physics. So that's the thing. Now, you can see how the statistics is going up. So run 1 or result ami paisu, run 2 aru 3 karone I probably this year result. Then run 4 aru 5, just starting to analysis has just been started. So thank you. Already almost there but it's really impossible. Undergraduate or karne shorten kora it's not possible. Really. So sorry for that. Thank you. Questions, Sagile, you can ask now. English.
Thank you.
It's not.
Thank you, Atanu. I think it was a very exciting talk, and congratulations for the achievement. I hope that you get the results that you desire. Okay, so now I would like to ask the participants to feel free and ask as many questions as you can. If you're facing network issues, maybe you can also type the questions in a chat box, and then we'll ask. Okay, so I think we have a question from Avinash. So he has asked. Yeah. Please go ahead, Atanu.
So the difference should be 5 sigma is not suggested. So কি হইছে মানে at least 5 sigma difference নহলে আমি কম যে it's not really different. মানে consider করা for example roughly at board নাই what it আছে no, it's not possible. But let's say মানে দুটা ball আছে, right? Two points, let's say 2 points. So দুটা point or image ললে resolution যদি বহুত বেয়া হয় তেতিয়া কি পয়েন্ট বিলাকৰ ইমেজ কেনেকুৱা আহিব এটা পিক্সেলেটেড ব্লবৰ নিচিনা আহিব, ৰাইট? দুটা পয়েন্ট, let's say there are 2 points, এটো ফটো লৈছো, তাৰ যদি ফোকাসিং নহয় ব্লাৰি ইমেজ আহে তেনেকুৱা কি হ'ব দুটা বলৰ নিচিনা কিবা এটা আহিব। And if the points are too close, এই দুটা বল almost এটাৰ মাজত এনেকুৱা সোমাই যাব, then we can really not say that এটা দুটা পয়েন্টৰ ইমেজ নেকি এটা পয়েন্ট basically. So like there is no difference between the 2 points. So you can think of like theoretical result and experimental results are like 2 points, and they're probably same. Theoretical result, experimental result almost same. Error iman dangor de ami khobo nuaru there are mane major difference ase niki nai. So in that case we cannot say really they are different. Tar mane notun physics lagibo, we cannot say that. Aru eta question ase, I'll come to that. So that means even a point duta jodi precise hoi ei tar major or even blurry thakileo point dutar major difference jodi bahut beshi hoy, then we can say they are different points, right? Otherwise both close hole resolution bahut bhal hole point hobo, then we can say the difference is large. So eta standard to lagibo, right? Man different hobo lagibo je ami precisely kobo paru যে they are different. So in sigma 2 hole amar is a blurriness tar around it pointer around is to blurriness that is like 1 sigma 2 sigma 3 sigma 4 sigma. So a distance itu jodi beshi no hoy 1 sigma jodi hoy then they will be like overlapping. 2 sigma hole olop touch kori thakibo, 3 sigma hole maybe they are 2 points, 3 sigma hole they are probably 2 points, 5 sigma hoi gole actually you can see that wow they are very different. And প্রথমেই মই কইছিল যে 5 sigma হলে কি হয় still etu chance je ei duta equal but eta error karone different boli lagise, but heitur chance hol 1 in a million, 1 in a million je amar mistake hoise. Okay, 5 sigma mane 1 in a million, but you can go to 6 sigma tetia tomar ki hobo aru precise ami aru confident that they are different. 7 sigma, oh we are more confident that they are different. So heitui mane jiman dangor hobo it's better and better. At least mane 5 sigma no hole ami physics ot consider koru je they are probably not different. Beleg field biology ba beleg as a social science or research bilakot euloke iman 5 sigma na jay aru horu difference hole euloke pai jay they are different. So amar particle physics we are really paranoid about these things. Ami mane really huge difference as a margin. Okay, next question. Yeah, the asking question. I missed that.
Yeah, so I think the next question is from Sikhamani. Yeah, she has asked about the existence of antiparticles and in fact what are antiparticles or antimatters are, and if they exist, where do they exist?
Okay. Every particle has an antiparticle, and this is an experimental fact, and they do exist. Turns out that in nature we have much more particles. So very good question. Aru etu eta amar physics or really dangor question. Je kio ami just particles pai thaku nature. It's almost always particles. We are made of particles, protons, electrons. Electrons are moving around protons, they're making atoms, molecules, and then we are. These are all particles. But according to, physics, according to symmetry, our particles are antiparticles same hobo lagise. Kio mane Big Bang tomaloke hunise probably. So Big Bang is like universe came out of nothing, right? And a burst we say. rough image, vague image, not completely correct in mathematics, formally, but roughly like an explosion. So nothing or pora, universe to ice. So nothing mane basically charge neutral, energy just energy pora, equal amount of particle, equal amount of anti-particle ice. So particle or anti-particle milide, they annihilate hoi photon hoi jay. They exist. Antiparticles are very common. We can produce them actually, and nowadays we produce them often. Eta photon, light photon loi, eta atomot inject korile high energy photon, electron aru tar antiparticle partner positron produce hoy, and we can detect them. So these are very common. But the big question in physics that where did those antiparticle from the beginning of the universe go? So it was a question. What goes? Asking to definitely. So that is not answered yet. Maybe you guys will do research and answer those questions. Next question. Yes.
Any career-related questions from the participants? Please ask. Don't shy away.
Yeah. Nainiki questions, career-related. Anyway, মানে এতিয়া নাথাকিলে মইতো আছো টিহু কলেজত বছৰত হিমাংশুক সুধিলেও হ'ব ইউ কেন চেণ্ড মি ইমেইল মই ইয়াত টাইপ কৰি আছো ইমেইলটো
So, or even you can ask in the Podartha Bigyanar Itukhito WhatsApp group.
Yes, in the WhatsApp group, yes.
So that is also one option. Yeah.
Yes. If you feel shy in a public group, also private, no problem. And I mean, you can sometimes visit Tihu College, and of course, we'll be organizing events together with Himanshu and
Yes, definitely,
others.
most definitely. Yeah.
And Aruhol, usually my lectures will record group. They are available if you want to follow.
Yes, that can also be shared.
Any other questions? Any now or later? That's okay for me.
Okay, anyway, so maybe we can proceed to. Oh, okay.
The question answer. Sorry, you said physics will change if the experiment predicts discrepancy greater than 5 sigma. Please say something more on that. So first, Tihu say physics will change it now. For example, a really famous example is our Newton or gravity. Newton or G m1 m2 by r squared. Newton or formula for force of gravity. Eta asil. Heitu apply kori bahut experiment ami korisu. Experiment korisu mane observe korisu. Gravitational karone experiment bilak already ase. Solar system ase. We can observe mane sunor mass kiman. Around at a planet ঘুরি আছে ওটার মাস যদি ইমান হয় then what should be the time period year or length কিমান হ'ব এইবিলাক shape কিমান কেনেকুৱা হ'ব আমাৰ orbital right so এইবিলাক ইউজ কৰি আমি ক্যালকুলেট কৰিছো Venus Mercury Earth এইবিলাকৰ orbit so there was no difference so result পাইছে experimentally the Newton's law ভালকে perfectly explain কৰিছে so তেতিয়া known physics কি আছিল Newton's law but around I think 1857 or something first time Mercury orbital all of discrepancy পাইছে মানে Newton's law apply করি যেনেকৈ orbit to হব লাগে it's slightly different orbit to নিজে ঘুরি থাকে not just it's orbiting the orbit itself is moving সেইটো Newtonৰ law explain নকৰে মানে slight difference আছে experimentally আমি যেটো পাইছো তাৰ লগত Newtonৰ law যিটো ৰিজাল্ট ক্যালকুলেট কৰিলে মানে থিওৰিটিক্যালি যিটো আহিব slight difference পাইছো so at that point we said that we need new physics Newton's law to enough নহয় new physics so later Einstein or general theory of relativity to hold our new physics at that time Einstein or general theory of relativity যেটি আইছে it explained exactly Mercury orbit কিয় এনেকুৱা কৰিব লাগে so right at this moment our known physics হল standard model বলি আমি জানো it includes all the electromagnetic theory wave interaction strong interaction gravitation and all the things this is our our standard known physics now we call standard model but এতিয়া যদি আমি experiment করি এটা discrepancy পাও just like Mercury orbit we say that we need new physics to explain this. So নতুন theory গুলো I hope I explain this. What I mean to say is that will there be a new fundamental force or something after its success? Yes, probably. Probably either fundamental force or not force, but unknown particles. Both possibilities are there. So yeah, there should be. Maybe we will not know what it is, but we will know for sure that we need that. We need a fundamental force or new particles to explain this. And maybe then some new theory will explain what are those new forces. What is the exact value of alpha? Exact value of alpha to roughly 1/137. Exact value is very long. I of course can't remember that. Exact value means up to this point, what is the value? So 137 plus blah 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 blah. It's a huge number. You can Google that. So 1/137 is roughly the bigger part. Then point tiny difference. Any other question? Okay, thank you. It was a good question. Okay. Are there any more values of spin other than half and minus half? Yes. Half or minus half nohoy. Half hi hoy spin. When it aligns along the magnetic field, we say plus half. When it aligns opposite to the magnetic field, we say minus half. But half is its internal angular momentum. So yes, there are zero spin, there are half spin, there are 3/2, there are 5/2, and many. And there are 0, 1, 2. So eta branch hole eneka integral spin ase 0 h cross, 1 h cross, 2 h cross, half mane half logo that h cross ase eneka aru eta branch hole half integrals. So half h cross, 3/2 h cross, 5/2 h cross, and so on. A non-integral bilak ami fermion boli jano aru integral bilak ami boson boli jano. You're welcome.
Yeah, okay. So if there are no more questions, I think it's time to wind up the show now. Yeah, so when to kindly present time.
There's an echo actually. It's from my
Yeah, I think it's coming from November.
Okay, is it okay? All right now?
Yeah.
Okay. Yeah, Apurva, please go ahead.
Yeah, I think we'll listen to the vote of thanks probably.
Okay, am I audible? Hello?
Yes. Please go ahead.
Yes, no.
To begin with, the talk is really an interesting one. Dr. Nath presented the interview of G-2 lab and the work being carried out there. He also discussed the basic concepts related to these particle physics in quite comprehensible manner. And I think this will be quite effective for the undergraduate groups and will be further helpful for them in future as well. For which I would like to express, I would like to thank the speaker for that effort, energy, and the time he lended. And I hope to carry out such events time and again. This event would not have been possible without the active participation of the aspirants as well, for which I am thankful to all the participants for attending the talk and giving their interest. And finally, I would like to thank the organizer to organize such event and to come up with the fresh talk in the series, or rather, I would like to say fresh series to begin with. And more such talks are coming again. So I hope all the participants will be present in the future talks as well. So thank you from my side on behalf of the organizing team once again. Thank you.